to individual version of the presentation for the final challenge, the mechatronic car. This is my team. We are Ricardo, Emilio, myself, and Diego Flores. The main purpose of our project is to design and implement a semi-autonomous control system for a small vehicle capable of dynamically adjusting speed and direction using PWM control, Bluetooth communication, and sensor feedback to achieve precise navigation and stopping distances. All of this aims to show our knowledge of mechatronic systems and automation, all of it following the SDG number 9. Some of the challenge requirements as listed in Canvas are that the vehicle design must be a four-wheel scale vehicle using Ackerman or differential steering. The control system must include a speed control, Bluetooth communication, and real-time feedback and distance monitoring. For the automation part, it must have acceleration, cruising, and deceleration phases to reach its target distance. We will talk about this further in the future. For its hardware configuration, we must use an STM32 microcontroller for regulating the sensors, actuators, and the data communication. It must have obstacle detection when follow the square path, and it must be able to operate in manual and automatic mode. So what is the proposed solution? This revolves around the development of a fully autonomous vehicle prototype designed to navigate independently. The system works with Bluetooth communication as well as multiple control loops through speed and direction adjustments. The vehicle operates autonomously in a pre-programmed trajectory while retaining the capability for manual control. The vehicle is built integrating a differential steering mechanism, which enables precise movement and maneuverability. The control system leverages an STM32F103C8T6 microcontroller, also known as the Blue Pill, which will act as the central hub for processing sensor data and executing control algorithms for both manual and automatic modes. What sustainable development goals did we focus on? I know we included 4 here, but the only one that we actually focused on during the development of the project was SDG number 9, as specified in Canvas, which is about industry innovation and infrastructure. And yeah. The main components of the car include 4 DC motors, because we are using a differential steering. It includes the Blue Pill or STM32F103C8T6. The power supply are the batteries shown above. These are 12-volt batteries with a battery capacity of about 5,000 milliampere hour. We're using an MPU 6050 from the different components it has. We're only using the gyroscope to control for direction control. We're using an LCD display for the display of variables like speed and position. We're using an HC05 Bluetooth module for communication. 2 H bridges to control the 4 motors in the car. We're using one encoder, which wasn't very precise, but we used it nonetheless, and an ultrasonic sensor. This is basically the schematic. We're using, on the right side is a representation of the main circuit, in which in real life we actually use 2 protoboards because it's huge. And you can see an example of the connected H bridge, the 2 motors. As I mentioned, we have 2 of those. Also the encoder, the 12-volt battery, um, how the 12-volt battery feeds into the H bridge, and the H bridge feeds the 5 volts into the system. We can also see the MPU for direction control, and we can also see right behind me the HC05 module. And on the left side of the screen, we can observe how the ultrasonic sensor and the LCD displays are connected. This is a pinout configuration. I do not think it's necessary for me to go into detail as to what each pin does, but if you want, you can pause the video and check. These are the general purpose input output configurations for pins A0 to A5, and then the I2C communication setup for pins PV6, 7, 10, and 11. Then the timer configurations using timer 4, channels 3 and 4 for the pins B8 and B9, and the USART communication configuration for pins 9 and 10. These are some pictures you can check for the assembly of the car to kind of match up how it looks with how it's supposed to look. As you can see, we put a lot of effort into it. Now, as to the control algorithms for distance and speed, they're defined in 3 stages: proportional control, feed forward control, and fallback safety mechanism. Basically, open loop, the prediction of the trajectory, and closed loop. This is the speed profile that we based our formulas on for our speed control. In our speed control, we actually ended up not using an encoder for feedback, for position feedback, but we will see that later. This is how it works when we're inputting a given distance and a given time. We first input the distance in millimeters, starting with the letter G. Sorry, followed by the number in millimeters, and then we get the feedback that the distance is received, and then we upload the time, and that is in seconds, starting with the letter H, and then we get the feedback that the time is received. For considering this trapezoidal speed profile, this is the formula that we use to determine the nominal speed, this total distance over half the acceleration time plus half the deceleration time, which happens to be the same in this case, plus the cruise time. This is how our trapezoidal speed profile actually looks when graphing the pulse width modulated signal for the motors. As you can see at the beginning, there's a spike, a huge spike. That is in fact part of the program, and it's there with the intentions of getting the car to move initially by just giving it a little boost, because we know that it's really hard to get the car moving at such low PWM signals. For example, like 300. It can be very hard to get the car moving, so we give it a little boost. And yeah, as you can see, it's pretty good. Then in here we have some videos which you can check directly with the presentation if you like. This is a brief flow diagram for the speed control. Basically, we input the command, we communicate it from the HC05 to the blue pill. We execute the void for distance and time control. We calculate the trapezoidal speed profile with pure calculations. We obtain time in DC variables to run the motors during the acceleration, nominal speed, and deceleration phases. And then we stop, we run the motors and we stop all motors. And then for the turn control, we have basically the same format. We just input a command for it to turn. It communicates the command from the HC05 to the blue pill. It executes the void for a 90-degree turn. It checks for the north with the NPU module, and then it activates the necessary motors to turn, which in any given case, if it wants to turn right, it will be the left motors, and if it wants to turn left, it will be the right motors. And it turns until the module says 90. If the module says 90, it stops. If it doesn't, then it activates the necessary motors to get to 90. We shared a lot of the learnings and challenges in class, but this was a very, very rich learning experience. I mean, talking about the whole semester invested into one single project, it was very tough. There were way too many challenges in the way. Um, it involved many sleepless nights and many failed dreams, but in the end we got it. We finally did it, and uh, a lot about automation, about integrating such different systems, and integrating a lot of theoretical knowledge into a practical project, like directly. And yeah, overall, it was a very rich learning experience. And thank you very much. That's all for today. Have a nice day.